All right, so moving forward, we're going to cover naming ionic and molecular compounds. This is going to be our last section before we open it up for just general questions and anything you guys have for us.
Yeah, all right, so first talking about naming ionic compounds. So starting off with this, it's good to know that naming ionic compounds comes in strictly two phases. Whereas first, you always want to start with the cation. Good thing to remember is that cations come first, starts with a C. It's positively charged, often is a metal. In two general rules of thumb are if the cation is a polyatomic ion, which essentially just means the ion's composed of more than one atom, i.e., ammonia, you write the name of the polyatomic cation as is. But if the cation is a transition metal, or a metal that has more than one oxidation number, you put the charge in Roman numerals after the metal in parentheses, which, as you can see on the bottom, there are some exceptions to this, but that's the general rule of thumb. Then once you've identified your cation and you know what you're doing with your cation, then you move on to your anions. The anions come second. These are most often negatively charged. They are negatively charged, and they are often a nonmetal. And these anions, as the element, you write the name of the element along with the suffix "ide" at the end of it. And if the anion is a polyatomic ion, you write the name of the polyatomic anion as it is after the cation. So again, like before with the sig figs, this is a lot of information, but this next slide we have a few examples kind of help you guys get into that. All right, so starting off with example number 1. So here we have KBr. Would anyone like to take a crack at trying to name this? I think I should probably potassium bromide. There you go. Nice job. I was going to give it away to you, but yeah, potassium bromide is correct. You start out with that metal, potassium K, and then you have that non-metal. You have the cation first, then the anion. That anion has a -1 form oxidation charge. That potassium has a +1. They cancel out to create that neutral compound. The non-metal gets the suffix of "ide," henceforth potassium bromide. Let's go to the next one. Anyone want to try this one out? Any guesses? Nothing is wrong, I promise. Okay, you definitely are getting very close, Rosario. It's knowing that this is, if you would like to reveal it for us, Alex, knowing that it is a one of those polyatomic ions that we were talking about. So SO4 is a sulfate, and as such, it carries a -2 charge. So when it's bonded to mercury, it creates mercury sulfate. Now, a good thing to keep in mind is recognizing that it's mercury 1, or Roman numeral for 1. And the reason why is you look at the sulfate and you go, well, it has no subscript of a 2 or 3 next to it, so it obviously didn't carry a charge. Not entirely. Technically, K and Br are K1 and Br1. But when it comes to mercury and sulfate, the mercury takes on that subscript of 2, and the sulfate, because the mercury carried a +1 charge, it takes on that subscript of 1. So that's why you have the Hg2SO4. Moving on to this next example. Would anyone like to take a crack at this?
Is it magnesium nitride?
There you go. Nice job. Yes, magnesium nitride is correct. You had that metal. There you go. Nice job, Haley. You had that first metal, that magnesium, right? We identified that was the cation. And we had that anion, the nitrogen. You add that suffix of "ide," and there you go, magnesium nitride. Let's move on to this 4th example. Yes, nice job, Haley, but you're missing something.
Oh,
Yeah, no, it's
you
all
didn't see that.
no, go ahead and reveal it. It's
Yeah.
titanium 2 chloride, because titanium is that transition metal and it carries that positive 2 charge. So that's why it's titanium 2. But nice job. You guys are getting it. Let's go on to this next example. This one's pretty hard, I know. Even the polyatomic ion is pretty rough. Give it another second or two. Should have told everyone in attendance to bring out a periodic table. That was our mistake. But we'll go forward, revealing it is tin 2 silicate. That SiO4 is a silicon polyatomic ion, and Sn corresponds to the element of tin. Therefore, all right, let's go on to the next one.
And don't be shy, guys. It's okay to get it wrong sometimes, because that's how you really learn. Is you get something wrong and you realize, oh, this is where I made my mistake. Let's not make that mistake again. So feel free, even if you're not super confident, to throw your ideas in the chat or say them, and we'll kind of like give you guys feedback on that.
Oh my, there you go. That is correct. Magnesium phosphate. I had faith. We'll move on to this next one. Just remember that transition metal rule when naming this one. Yeah, stemming off of earlier, I know that even us tutors included. There you go. That's correct. Mercury 2 oxide. Even us tutors ourselves are keen to get things wrong every once in a while. Actually, more often than not.
Would you mind going over one more time why it's Mercury 2?
Yeah, for sure. So the reason why it has that 2 instead of the 1 like the first one is because of that formal charge that Mercury has. So you know how oxygen has a -2 charge? What's happening in this compound here is that Mercury is supplying a +2 charge to have that overall charge be 0. So it's called Mercury 2 because there is a formal 2 positive charge or +2 charge on that Mercury. Whereas with the sulfate, like Isaiah was saying, sulfates have a -2 charge. And in this case, we have 2 mercuries to counteract that, which means that each mercury has a +1 charge. So it has the Roman numeral just 1 there. Because transition metals can have different states. Like titanium isn't always going to only have a +2 charge. It might have a +3 charge. And they show that by having the parentheses around it. Because titanium with a +2 charge results in a different compound than if it had a +3 charge.
I see. That makes sense. Thank you.
Yeah, all right. Nice explanation, Alex. Now on to this third one. Very, very close, but yeah, you're right on there. It is cobalt 3 phosphate. Just get to know. But you guys are definitely on track with this. And then on to our very, very last example. I know that polyatomic ion is.
I have a comment. So since all of these are monatomic ions, correct?
Yes.
So that, okay, that makes sense because like ATE, you have to change the suffix of the ending.
There you go.
Okay. And then is it always IDE, ITE, and ATE
Yes.
for the monatomic? Always? Okay. Thank you.
Yeah, no problem. I'll actually give a hint on this last one. That polyatomic ion is an acetate. Any bites? It's okay if not. There you go. Nice. It's like chromium 2 acetate, but yeah, nice job. All right, that kind of concludes ionic compounds. Let's move on to molecular.
Yeah. Did you guys have any questions before we move on? Because the naming can be really tricky. So
Can you explain the last one, please?
Yeah, sure. Okay, so the acetate polyatomic ion is C2H3O2, and it carries a +1 charge. So that being said, we have chromium 2, because as you can see, that acetate has that there's 2 of them. It has that subscript of 2. Maybe, Alex, I'm thinking of going into Paint and showing them assigning formal charges and bringing them down when forming together compounds.
yeah, did you want me to stop the screen share real quick?
Yeah, let me pull up really quick.
Okay, let me see. Where is? Okay, I lost the little bar at the top that shows me how to stop the screen share, and that is unfortunate.
Let me see. I think I'm able to do it. All right. Do you guys see
Oh,
my
there we go.
paint? Is my MS Paint visible?
Yeah, I see it.
Okay, awesome. So let's do that example from earlier, that Mercury Two Oxide. I think that's a pretty good one. So we have mercury, right? So we know that it was Hg. Apologies for this. It was Hg and then O. So thinking about our oxidation numbers and that charge that oxygen normally carries, we know that oxygen normally carries that -2. Right? And we know that if this is a neutral compound and there's no charge on the compound itself, then everything has to equal out to 0. So then we can kind of take this as if it's an equation. And we're trying to cancel these out to 0. We have this charge right here that we don't know, and we have this charge here that we do know. So we know that 0 is going to have to equal, oh, that's a 6. We know that 0 is going to have to equal x minus 2. This is x. So then we can solve for x, where we know that x is also equal to 2. So if mathematic, if mathematic expressions and that sort of visual aspect is really how you learn, this is a good way to make sure that you always get those charges right and can name these transition metal compounds efficiently. This rule of thumb genuinely works every single time. I still use it to this day.